So last time we had done moment of inertia, and I have just been told about your coming tests in school, I guess. Okay, so your syllabus needs to be completed. So this chapter is yours. The end of this chapter is your last part, है ना? The syllabus is still system of particles and rotational motion. Okay, so I will try to complete this chapter today. Okay, because that is why we have two physics classes. Okay, so one will be now So I think somehow I got disconnected. Now, am I audible to everybody? No.
Yes, sir.
ठीक है, just a minute, just a minute. ठीक है. Is the screen visible? Is the screen visible to everybody?
Yes, sir.
ठीक है. ठीक है. Now, I thought I was connected, so I taught these many things. But ठीक है, let's start again. ठीक है, I don't think anybody till where I had taught you. I guess from the starting only. ठीक है. No problem. ठीक है, we will do it from the starting again. ठीक है. So, angular momentum. ठीक है, we are going to talk about angular momentum. है ना? So, angular momentum is the rotational analog of linear momentum. ठीक है. Whatever is the use of momentum in linear motion, ठीक है, that is the in rotational motion, the same use is shown by angular momentum. ठीक है. Use means what? Like in linear motion, you said that rate of change of momentum creates force. ठीक है, in linear motion. So in rotational motion also, rate of change of angular momentum, ठीक है, rate of change of angular momentum will create angular force, rotational force. ठीक है, that rotational force is called as torque. ठीक है, we will see that after this also. ठीक है. So in that manner only we are able to compare. Okay, we are able to find a relation between linear momentum and angular momentum. Okay. So if it is a rotational analog of linear momentum, what I can say is that linear momentum is written as P is equals to m into v. Okay, linear momentum is mass into velocity. So since it is analogous, what I can do is I can start to replace the values. Okay, linear momentum is replaced as angular momentum. Okay, linear momentum can be replaced as angular momentum. Mass, okay, I have already told you the rotational analog of mass is what? It is moment of inertia. So instead of mass, I will replace it with moment of inertia. Okay. Yesterday I had no class in ESIP.
So he is
Yesterday,
from coaching batch.
acha, he is from 11th batch. So I guess it was recorded. I had recorded the yesterday's lecture. Okay, maybe you are viewing it from a tab, okay, or a mobile, okay, so you can't access it. Okay, to access that lecture you need PC. Okay, you need a laptop or a PC. So if you don't have it, then ask any of your friends to provide you with the lecture. Okay, they can download the lecture also. Okay, so I also don't have a PC, so I also cannot provide you with that lecture. No. Yes, yes. नहीं iPad में भी also you cannot access it. Okay, even in iPad you cannot access the recorded lecture. I also have an iPad. I also try to access it, but I am unable to do it. Okay, so to access the recorded lecture, you need a laptop or a PC. Okay, so if you have any friends or anyone who has a PC or a laptop, okay, just contact them. They can download it. Okay, it is not a very big file. 1.5 hour class is around 300 to 400 MB. Okay, so you can just download it and take from your friend. Okay, you can just share it on your drive or anything. Okay, so that is one possibility which I can tell you. Okay, because I also don't have a PC, so I also cannot do anything about it, and I also don't have a laptop here. But just see, okay, if you are able to get the lecture from somewhere. Okay. Acha. So let's come back to this angular momentum. We have to complete this chapter today. Okay, try completing it.
So, sir,
So yes,
so was yesterday's class a revision class?
yes, it was a revision. See, actually on Sunday, whatever class I keep now, that is only for those students who have missed the classes. Okay, or you can say who joined late. Okay, so I am teaching the same thing. Okay, I have done integration, differentiation, motion in straight line only I am doing. So these are things which are already done. So it is for only those students who have joined late. Okay, not for everybody. Okay, it is not a revision class. It is a backup class, you can say. Okay, for those who have missed or joined late. Okay.
Okay, sir.
Yeah. ठीक है. So where was I? Linear angular momentum. Let's come back over here. Okay, we will discuss that later on. Today I have to finish the chapter. Okay, let's just try to finish it because your test is coming. Okay. So see, angular momentum is rotational analog of linear momentum. So what I did is I am trying to derive a formula, write a formula for this angular momentum. Okay, I am trying to write a formula for angular momentum. Okay, so what I do is first of all I write the formula for linear momentum. P is equals to m into v. Now what I do, I start replacing it with the rotational analogs. Okay, I start to replace it with the rotational terms. Like linear momentum is converted into angular momentum. Okay, so P is replaced with L. है ना? Yogendra sir is I don't know if he's very sick or not, but yes, he is a little bit sick. He is a little bit ill. Okay, so that is there. Okay, so exact condition also I also cannot tell, but yes, he is a bit sick. Okay, acha. So where was I? Huh. uh, Angular momentum, sorry, linear momentum is replaced with angular momentum. Okay, your mass, okay, the mass is replaced with moment of inertia because it is the rotational analog, it is the rotational equivalent. Okay, so it is the rotational analog, so moment of mass is replaced with moment of inertia. And same for velocity, linear velocity is replaced with angular velocity. Okay, so linear velocity is replaced with angular velocity, it is omega. So the formula of angular momentum comes out to be I omega. Okay, L is equals to I omega. Yeah. Now suppose you want to let's see an example. Okay, how better you can understand this. Okay, forget all this. Okay, now if you want to understand this, just see this example. That suppose I have a disk, and the disk has some mass m and radius r. Okay, there is an axis passing through the center of mass of the disk, and it is rotating with angular velocity omega. If it is rotating with angular velocity omega, it must be having some angular momentum. Okay, it is very much similar to linear momentum. If a particle is having velocity, it has linear momentum. So in the same manner, if a particle is having angular velocity, the particle or the object, okay, it will be having angular momentum. So this disk, since it is rotating with some velocity, okay, angular velocity, it must be having some angular momentum, है ना? And we have to calculate its magnitude. Okay, so let's calculate its magnitude. I have just told you L is written as I omega. Okay, I is what? I is the moment of inertia about the given axis. So the axis, since it is passing through the center of mass of the disk, so I can write it as the moment of inertia of the disk about its center of mass. Okay, I have already told you the different values of moment of inertia about the center of mass, okay, of the standard shapes. So for a disk, the moment of inertia about the center of mass is how much? It is mr square by 2. It is mr square by 2. And the angular velocity of the disk is omega. It is given in the question, so I can just replace it with omega. So the formula, so the not the formula, the result of angular momentum comes out to be mr square omega by 2. Okay, it comes out to be mr square omega by 2. This is the angular momentum of the disk. Okay, acha. Now if rotational quantities are given to you, well and good. Okay, if rotational values are given, like angular velocity is given, moment of inertia is given, okay, if these are values are given, then it is fine. Okay, you can calculate the angular momentum using I omega. But what if what if you have a object, okay, you have a particle, suppose, of mass m and linear velocity v going in a circular track of radius r. Now how will we calculate the moment of angular momentum? Okay, because it has some velocity, it has some angular velocity also, and it will be going around the circular track also, so it is showing also. So if such a situation occurs, you can say that the values which I know, okay, values known to us, the values given to us are linear values. Okay, I have been given linear velocity, I have been given the mass. Okay, these are all linear values. Angular values are what? Angular velocity, moment of inertia, these all things. Okay, so a simplified formula, a better simplified formula for angular momentum can be calculated over here. Okay, what is that? That angular momentum I have written as I omega. Okay, angular momentum is written as I omega. So let's see. In general, if I want to write angular momentum, okay, if I want to write angular momentum for a point mass, okay, so the moment of inertia for point mass in general formula is what? It is mr square. In general, I am talking about. It is mr square. Okay. Acha. If this is mr square, omega can be written in terms of linear velocity. How? V is equals to omega r. You know this. Okay. V is equals to omega r is true for any circular motion. You must have done this in circular motion in plane. Okay. So here you can say omega is what? V by r. Omega is what? V by r. So this can be replaced as V by r. V by r. Okay. So here r gets cancelled. So you have see r into mv. R into mv. है So if you see the angular momentum can also be written as the radius r into linear momentum p. R into p. Okay. If you try to represent it as a vector, it comes out to be L vector is equals to R cross P vector. Okay. If you write it in vector form. Okay. In vector form, it becomes R cross P or R into P if you are writing the magnitude. Okay. RP sine theta. In most of the cases, you can see that momentum and R vector are perpendicular to each other. So sine theta becomes 1. Sine 90, so 1. So in the most of the cases, R cross P comes out to be RP only. Okay, so angular momentums, another formula is R cross P. Good morning, good morning. Okay. Acha. Now see, once I have determined that angular momentum is R cross P, okay, there is a new, a new definition for angular momentum. Okay, whenever whenever a linear quantity whenever a linear quantity is cross multiplied with r vector, the radius vector, okay, it is called as the moment of that thing. Okay, like in this case when I have written r cross p, it is called as moment of momentum. Moment of momentum. Okay. Suppose I would have multiplied it with r cross m. Okay, m is not a vector quantity, so cross does not have a meaning over there. But still, just for similarity purposes, okay, just for just comparing it. Okay, if I write r cross m, it will be represented as moment of mass. It will be represented as moment of mass. It will be said as moment of mass. This is the name of the value. R into m is moment of mass. R into p is moment of momentum. If I write r into f, r cross f, this is written as moment of force. This is called moment of force. So whenever a linear quantity, see, if you see, all these three are what? These are linear quantities. Whenever a linear quantity is cross multiplied with r vector, okay, whenever a r vector is cross multiplied with these linear quantities, that new term which is generated is called as moment of that linear quantity. Moment of momentum, moment of mass, moment of force. Yeah. Yes, any doubts? Okay. Please mute your mics. If you don't have doubt, mute your mic.
Excuse me, sir.
Yes.
What is that R vector means?
R vector is the radius vector. Here see. A particle, this is the center. A particle is at A, B, D, E. Okay, the particle will be moving in this direction. Okay, particle will be moving in this direction. So you can see here that when the particle is at A, its position can be represented as R vector, radius vector. Okay, when it is at B, again the position is R vector. See, when it is at D, R vector, E, R vector. So you can see that the R vector is rotating. R vector is rotating. ठीक है, the r vector is having the same magnitude but it is changing its direction continuously with the object, with the particle. ठीक है, so this vector is called as r vector, है ना, the radius vector.
Understood, sir.
Yeah, ठीक है. So these are the basic terms used. ठीक है, moment of momentum is called as angular momentum.
So
Angular
please,
momentum. Yeah, just a minute, just a minute. Let me write this momentum. ठीक है, moment of momentum is called as angular momentum. Moment of mass has no specific term. Moment of force is called as torque. ठीक है, we will study this torque again. It is coming out again and again. ठीक है, so we will see this, and don't worry, just have patience. ठीक है, so there are two formulas for angular momentum. ठीक है, you have to remember both the formulas. Is I omega, other is R into P. ठीक है, I omega will be used when rotational values are given to you. Suppose rotational velocity is given, angular velocity is given, ठीक है, moment of inertia is given, so I will use I omega. But if linear values are given to me, linear values means linear velocity is given to me, mass is given to me, है ना, so in that case I will use R into P. I will use R into P. ठीक है, so let's see a question. ठीक है, you will understand it better through a question. So just write this, then we will do a question on it.
done, sir.
Done. ठीक है, let's see a question. ठीक है, this is the question that there is a car on a circular track. ठीक है, the radius and speed is given and the mass of the car is given. So here you can see easily see that the values which are given to me are all linear values. ठीक है, linear velocity is given to me, mass is given to me, radius is given to me, so these are all linear values. ठीक है, if angular momentum, moment of inertia, these things would have been given to me, I will say that angular values are given to me, angular values are given to me. So in this case, if I have to find the angular momentum, okay, so what I will use, I will use the formula of R into P, R cross P or RP sin theta. Okay, if we just need the magnitude, so it can be written as RP sin theta. Okay, now see, if you draw the motion, if you draw the motion of the car, okay, this is R vector, that is how much it is, 100 meters. 100 meter, here is the car, it has a velocity of 60 meters per second. Okay, when you write R cross P, you can write it as RMV sin theta. Okay, so what is this theta? Theta is the angle between velocity vector and R vector. ठीक है, theta is the angle between velocity vector and r vector, radius vector. So here you can see that the velocity is in this direction, it is in the y direction, and the r vector is in the x direction. So angle between v vector and r vector is how much? It is 90 degree. It is 90 degree. So if it is 90 degree, so you can write theta as 90 degree over here. If you write theta as 90 degree over here, sine 90 is 1. Okay, it will come out to be 1. So you can write angular momentum directly as r m v, r into m into v. This will be the magnitude of angular momentum. Okay. Acha. R is how much? 100. Mass is how much? 300. Velocity is 60. So this comes out to be 18 into 5, 10 raised to power 5 kg meters per second. Kg meter square per second. Okay, so this is how you write angular momentum. Okay, this is how you write angular momentum. Okay, you can write it as 1.6 into 10 raised to power 6 also, same thing. It doesn't matter. Okay, so whenever linear values are given to you, use r cross p. Whenever angular values are given to you, use I into omega. Okay, this is how we differentiate between the formulas of angular momentum. Okay, let's see an example. Let's see another example. Okay, if you want, you can write this.
Sir,
Yes.
from where did you get the sine theta?
Sine theta, I told you, na, it is r cross p. It comes out to be r cross p because L is a vector quantity. Na? When you are writing it r into p, that means r is also a vector and p is also a vector. Okay? If r and p are vector, either it will be a dot product or it will be a cross product. Okay? When I write L as r into p, I know that r is also a vector, p is also a vector. So here either it will be dot or it will be cross. Now if you keep it as dot, suppose you wrote r dot p. Okay. If you write r dot p, the result should be a scalar quantity. But the result is what? The result is vector quantity. So it cannot be a dot product. It has to be a cross product. It has to be a cross product. So that is why there is a cross product. And by the definition of cross product, when I write its magnitude, it comes out to be rp sine theta. Okay.
Okay, sir.
Then after that, it is just simple. Just see the diagram. Okay. From the diagram, you can tell what is the angle between r vector and p vector, or the velocity vector. Same thing. Okay. The velocity vector and momentum are in the same direction. So that is why whatever is the direction of p vector will be the direction of linear momentum. So linear momentum is in the y direction, r vector is in the x direction. So I can safely say that in our question, theta is how much? It is 90 degree. So if theta is 90 degree, if I replace 90 over here, it becomes sine 90. Sine 90 is 1. Sine 90 is 1. So that is why that term vanishes. Okay. Acha. Now let's see another problem. Okay. In angular momentum only. Okay, it is angular momentum only. Okay, a small variation is there. A small variation is there. Suppose this is x, this is y. A particle is moving on a straight line. Okay, a particle is, yes. Okay, suppose a particle is moving in a straight line. At some instant, at some point, okay, at some time, the particle is at this position. Okay, the coordinates of this particle is, let's say 3,4. Okay, the coordinate of the particle 3,4. Okay. And the mass of the particle is suppose 10 kg and it is moving with a velocity of let's say 10 meters per second. Okay, just for example, I'm saying. Now, if the particle is moving like this on a straight line, okay, about a point O, about the point O, I have to calculate my angular momentum. What is the angular momentum about point O? This is the question they are asking. Okay. So if they are asking me the angular momentum about point O, that means first of all they have given me linear values. Okay, let's see the formula and we will move further on. Okay, using that formula. So angular momentum has two formulas. One is I omega, other is R cross P or RP sine theta. RP sine theta. Okay, so these are the two formulas which I can use. Now in the question is anywhere given to me what is the angular velocity or what is the moment of inertia? No. Okay, it is not given to me. Okay, I cannot calculate that anywhere. So if I cannot calculate that anywhere, so this will be not used. I cannot use the first formula. Okay, I will use the second formula. I will use the second formula. Now, if you are using the second formula, what you need is you need the r. Okay, you need the r vector. Okay, magnitude of the radius, and you need the momentum. Okay, you need the momentum. So momentum is easy to calculate. P can be calculated as m into v. M is how much? It is 10. V is how much? It is 10. So this comes out to be 100. Okay, it is kg meters per second. Uh, uh, Linear momentum is 100 kg meters per second. No doubt in that. That is okay. Okay, no problem. I have the momentum. What about the r vector? R vector is what I told you. R vector is the distance between the particle and the center. Okay, here the center is my origin. Okay, here the center is my origin. In the previous case, my center was the center of the circle. Okay, that is why I was calculating r from this point. Okay, it is not mentioned anywhere. It is understood, during a circular motion that my center is the center of the circle. But when a particle is moving on a straight line, the center is defined by the question. Okay, how they say they find the angular momentum about a fixed point O. That fixed point is your center now. Okay, so if this point is your center and your particle is over here, if you want to write the radius, okay, the radius will be what? Radius will be this vector. R vector will be like this. Okay, R vector will be like this. Now what you need is, see, you have calculated momentum. Just see if I try to rearrange it, if I try to rearrange this formula, just see a very unique thing will happen. I can write it as r sine theta into p, because p I have already calculated. I have not calculated sine theta or r. Okay, so if I rearrange this, I can write it as r sine theta into p. I can write it as r sine theta into p. So just see here, what is theta? Theta is the angle between r vector and p vector. P vector is what? P vector will be like this. P vector will be like this. R vector is like this. So angle between r vector and p vector, if you see, okay, for calculating the angle between r vector and p vector, you will have to move the r vector forward. Okay, why you have to move r vector forward? So that their tails coincide. Okay, when you move r vector forward, it will come out to be like this. Okay, r vector moves forward, their tails coincide now. The r vector tail and the p vector tails are coinciding now. So angle between these two is this angle theta. This angle theta. Hai. So angle between r vector and p vector theta is this. If this is theta, this angle will also be theta. Okay, if this angle is theta, this angle will be 90 minus theta. This angle will be 90 minus theta. Now what you can say is I can create two components of R. Okay, R vector now has two components. One component is with the angle R cos 90 minus theta, and the other component is this R sin 90 minus theta. Sin 90 minus theta. Okay. R cos 90 minus theta is what? R cos 90 minus theta is R sin theta, R sin theta, and R Sine 90 minus theta is r cos theta. So basically, if I draw this diagram again over here, just wait a minute, I will show you that figure also again. Okay, just have patience. What I have is, I have my momentum in this direction. Okay, I have my momentum in this direction. This is r sine theta. This is r. This is r cos theta. This is r cos theta. Now, basically, what you can say is that you want to find angular momentum. Angular momentum is basically the product of r sine theta into momentum. Okay, so what is r sine theta? R sine theta can be written as the r perpendicular to your momentum. Okay, r sine theta is the radius, component of radius perpendicular to the momentum vector. Okay, so therefore another perspective of angular momentum, formula is same, formula has not changed. Okay, just the viewpoint to observe it, just the viewpoint to see it has changed. Like now I can write angular momentum as r perpendicular into p. R perpendicular into p. What is r perpendicular? It is the radius vector. R perpendicular is radius vector perpendicular to momentum vector. Okay, so if you see here, if you see in the question, okay, they have given to us 3,4. Okay, they have given to us 3,4. What is 3? 3 is just a minute, huh? 3 is what? 3 is this distance. Okay, on the x-axis, the x coordinate is 3 and the y coordinate is 4. Y coordinate is 4. So you can see that this 4 and r sine theta are parallel, and also both are perpendicular to the p vector. Both are perpendicular to the p vector. Okay, so without any of the calculations of sine theta and all, okay, without even calculating sine theta, would have directly said that r perpendicular in this case is how much? It is 4. Momentum is how much? You have calculated it as 100. So angular momentum will be 4 into 100, that is 400 kg meter square per second. Is this clear? Okay. About point O, if you see, okay, from the point O, if you see, R vector has two components. One component is perpendicular to R. One component is perpendicular to P, and other component is parallel to P. Okay, you could have written R cos theta as R parallel also. No problem. Okay, we don't have to do anything. We don't have to deal anything with R parallel. Okay, we don't have to do anything with R parallel. We are only interested in R perpendicular. Why? Because R perpendicular is represented as R sine theta. And as per the basic formula, R sine theta is used, not R cos theta. That is why we are not using R parallel, we are using R perpendicular. Is it clear? Any doubts, anybody? See how there is angular momentum. Just try to observe. Okay, suppose you are standing at one place. Suppose you are standing at one place and a train is moving from left to right. Train is moving from left to right in front of you. Okay, so how will your head move? You are not moving anywhere. How will your head move? Your head will move from left to right in a circle. Your head will move from left to right in a circle. So for you, for the observer standing at point O, for an observer standing at point O, he will see the particle in circular path because your head is going in a circle. Okay, so you can say that when my head moved from 0 degree to 90 degree, the man moved from A point to B point. Okay, it is like this. Suppose the particle moved from A to B like this. A to B. So what is happening? It is creating an angle over here, na? It is creating an angle over here. So any motion can be converted into angular motion. Okay, you can calculate the angular momentum for almost any case. Okay, only one case is there in which angular momentum will be zero if the observer is standing at point A only. Okay, if the observer is standing at point A, the particle will be going in the straight line. Okay, in a straight line, your head won't turn anywhere. Okay, if your head is not turning anywhere, you are saying that it is not showing angular motion. My head is not showing any angular displacement. Okay, so if my head is not showing any angular displacement, it is not showing angular motion. So in that case, the angular momentum will be zero. Okay, but if the point is somewhere else, है ना? हाँ. But if the point is somewhere else, then definitely your head will move. Okay, your head will turn. If it will turn, it will show some angular displacement. If it is showing some angular displacement, then definitely there will be some angular velocity connected with it. If there is some angular velocity, it has some angular momentum. Simple. Okay. And so that is why even a linear motion is showing angular momentum. Okay, linear motion, you are saying linear motion, I am saying it is angular motion. Just a frame of reference. Okay, rest and motion, this is a concept of rest and motion. You will be saying that you are at rest on your in your home, but a man on moon will say that you are moving with the earth. Okay, so it is just a concept of frame of reference. Okay, for me, I am seeing the particle on a straight line, but for an observer standing at point O, he can see that the particle is going in, showing some angular displacement. It is showing some angular velocity. Hence, it is showing some angular momentum. Okay, so in this manner, it is defined. Okay, if you are not getting it, don't worry. Okay, nobody is going to ask you कि sir straight line में कैसे it is showing angular momentum, है ना? You just need to know how to calculate angular momentum. Okay, in exam also, they are not going to tell you to describe, right? How can you see your angular momentum in a linear motion? Okay, so don't worry about such things. Okay, you are preparing for a competitive exam in which they don't ask you such questions. Okay, luckily it is MCQ. They don't ask you such questions. Okay, so don't worry about these things. ठीक है. And so hope everybody has written this. Okay, just for satisfaction, I am going to give you another question.
Will you scroll up a little bit?
Yes.
Thank you, sir.
A little more up.
Thank you, sir.
What? Done. Yes.
Yes, thank you, sir.
I cannot get what you are saying. Your voice is very disturbed. ठीक है.
Done, sir.
Done. ठीक है. Just for satisfaction, I am going to give you another question. ठीक है. Try to solve this. Very easy. ठीक है. Again, it is very easy. ठीक है. Your particle is at observer is at O, and now your particle is going like this. ठीक है. In a vertical line. Where is the vertical straight? ठीक है. And your particle is at -4,3. Mass is 5 kg and its velocity is 3 meters per second. ठीक है, again the particle is going along a straight line. ठीक है, its mass is this much, its velocity is this, and at this instant the particle is at -4,3 point. ठीक है, it is at this position. Again you have to find the same thing. What is the angular momentum of the particle about point O? ठीक है, I just need the magnitude. There is no need for calculating the direction or not. You just need to calculate the magnitude. So what should be the answer? Anybody? Very easy question. Yes. Anybody? इतना time? 60. Very good. Brilliant. ठीक है. 60 is the answer. How? ठीक है. How 60 is the answer? Simple. Angular momentum. I just told you how do we write angular momentum about a fixed point? R perpendicular into P. R perpendicular into P. You can see that P will be in the direction of velocity. Yes, 60 is the answer. ठीक है. P will be in the direction of velocity. Simple. है ना? Now R vector will be this. R vector will be this. One component of R vector is this. Other component of R vector is this. So this is -4. This is 3. Okay, as per the coordinates, we can see that it is -4 and 3. So simple. The 3, you can see the 3 component is parallel to P vector. So we won't use this. Okay, but -4 is perpendicular to P. -4 is perpendicular to P. You can see that since it is perpendicular to P, I can use that. So R perpendicular will become 4. Okay, I just need the magnitude. I am not interested in the direction and all. I just need the magnitude. So I'm writing it as 4 only. Okay, not -4. Into P. P is how much? M into V. 5 into 3. M into V. So this comes out to be 20 into 3, 60 kg meter square per second. This will be the angular momentum about point O. Okay, so this is how you write angular momentum in very simple manner. Okay. Acha. Now, I guess everybody is clear with angular momentum. Okay, there are 3 ways you can say in which you can write angular momentum. One is I omega. Okay, whenever you have rotational values, you use I omega. If you have linear values, you use R cross P. Okay, you use R cross P. If a particle is moving in a circle with linear values, use R into P. है ना? And if it is moving in a straight line and you have to find the angular momentum about a fixed point, then you use R perpendicular into P. It is the same formula, just extension of that formula, you can say. Okay, so just for your convenience, I am saying that there are 3 formulas. Okay, so these are the 3 variations which can be created, you can say. Okay, acha. Now let's move on to torque. Okay, torque is represented by tau. This is called as tau. Okay, the spelling is TAU, tau. And it is not T, it is not U also. Okay, it is somewhere between T and U. It is the combination of that. Okay, so it is called tau, like this. Okay, this is the representation, just a representation symbol of torque. Acha. What is torque? Torque is the rotational analog of force. It is the rotational analog of force. Okay. So just now I told you the rotational analog of linear momentum. So in the same manner, rotational analog of force also has to be there. That rotational analog is called torque. Okay, torque is something which has the tendency to create linear rotational motion. Okay, torque is a quantity which has the tendency or which creates rotational motion, just like force. Okay, force also has either the tendency to create linear motion or it just creates linear motion. Okay, if you apply force somewhere, it either moves in a straight line, or if there is friction and all, okay, there will be a tendency to create linear motion. So in the same manner, torque is also there for rotational motion. Okay, if there is a tendency to create rotational motion, it will create. Okay, so torque is just the rotational analog of force. Okay, so just now I had written that torque can also be called as moment of force. Moment of force. Yes, torque can also be called as moment of force. I just written it just before now in angular momentum. Okay, so you already have a formula for torque. You already have a formula for torque. That is R cross F. Okay, if force is given to you, and you are trying to create a rotational motion from that. Okay, how? In case of door. Okay, just see your practical example, your door. What do? You apply a force. But when you are applying a force, the door is showing what? The door is showing rotational motion. So what is happening? Your linear force is somehow is converted into torque. It is converted into rotational force. It is converted into rotational motion. That is torque. That is torque. Okay. Whenever you are seeing a rotational motion, that means there is some torque associated with it. Okay, so one formula is this, that torque is equals to R cross F from the basic definition, moment of force. Okay, moment of force is called as torque. Okay, so you could have written it as RF sine theta, sorry, RF sine theta. So again the same thing. Okay, RF sine theta. Okay, I told you in the previous one that when it is written as RP sine theta, you could have written it as R perpendicular into P. You could have written it as R perpendicular into P. So same thing here also. Okay, RF sine theta can be written as R perpendicular into F. R perpendicular into F. Okay, we can take directly the component which is perpendicular to the force. Okay, instead of taking the total R vector, we can only take the perpendicular component of R. So R perpendicular in case of force is also called as lever arm. Okay, it is just a term. It is just a term, lever arm. Okay. If somewhere in questions they say that the lever arm of the force is 3 meters, so you should know the meaning. It is just representing R perpendicular. That's it. Okay, it has no other meaning. It has no other sense. It has no other hidden, quality or something else. Okay, lever arm just means R perpendicular. That's it. Okay. Acha. Now see, this is one definition. Okay. Acha. There is another definition for torque. When we will see questions, you will get a clear idea of what I am trying to do here. Okay, but just wait a minute. Let me just define the formulas over here. Okay. So another definition can be derived from, you can say, the analog. Okay, it can be derived from analog, that you write linear force as dp by dt, or m into a. You write it like this. Okay, m into a or dp by dt. So using this analog, okay, using the analogous method, okay, what I can say is that the force will be analogous to torque. So it can be written as tau vector, torque vector. This is equal to d by dt. Time does not change. Time is same in rotational motion also, in linear motion also. But your linear momentum is converted to angular momentum. Okay, your linear momentum is converted to angular momentum. So rate of change of angular momentum gives you torque. I just told you this in angular momentum also. Okay, so dl by dt is torque. This will be equal to m into a. The rotational analog of mass is what? It is I, moment of inertia, and acceleration is what? It is alpha. So torque is equals to dl by dt, or I alpha is another formula for torque, is another way to calculate torque. Okay. So again you can see here, again it is similar to your this angular momentum. The way in which angular momentum can be defined was two ways. One was using linear values, other was using angular values. So here also see, when you have linear force, when you have r vector, you can use the first formula. When you have angular values like moment of inertia, like angular acceleration, you can use I alpha. You can use I alpha. Okay, so this is how you define torque. Torque is defined in two manners. One is linear, one is angular. Linear, it is defined as r cross f, or r perpendicular into f, and angular is defined as I alpha. Okay, I alpha. Okay, so these are the two ways in which you have to remember this torque. Okay, just you have to keep in this mind. Okay, any doubts? Okay, if you have any more doubts, it should get cleared in further examples. Okay, we will see some examples over here. Let's see. You will get a more better idea of what I am talking about. Okay, so let's see. Let's see examples, questions. Okay, now see here. Whenever on an object, I write this cross sign. Okay, I write a cross sign over here like this, in which I have drawn here. It means that it is hinged. It is hinged. I guess everybody knows the meaning of being hinged. Okay, your door is hinged to the wall. That means it is fixed at that point. Okay, where the door and wall are meeting, you must have seen hinges are applied. Okay, so hinges are what? Hinges are those points which are at rest at all times, but the objects around it, okay, the objects which are there around it, they show rotational motion. Okay, they will show rotational motion. It is like you have fixed it with a nail. Okay, you have just applied a nail at this end. And now see, if I apply a force, like this, okay, on the rod, okay, what will happen? What should happen? The length of the rod is L. What should happen? You can understand that the rod will start to rotate like this. And it will start to show a circular motion in anti-clockwise direction. You can see that it will start showing anti-clockwise direction motion. Okay, so if it is showing some motion and force is being used to create that motion, then there must be some torque. There must be some torque associated with the rod. There must be some torque associated with it. Okay, what is that torque? That is only what we have to calculate. Now here you can see that the value of force is given to us. So if value of force is given to us, that means linear values are given to me. If linear values are given to me, I can write torque as r into f, r perpendicular into f, in fact. Okay, r into f, when you are writing, you have to write rf sine theta. Okay, but let's write it better to write it as r perpendicular into f. Okay, so r perpendicular, if you see here, f is in y direction like this. Okay, f is in the y direction. At point O, this is point O. Let's suppose the point of hinged point is point O. From point O, the perpendicular distance of force is, you can see, it is this length. This length is perpendicular. Okay, what is that length? That length is L vector, or L. So normally L, not L vector. is L. Okay. So if it is L, you can safely say that the torque is L into F. This is the magnitude of the torque in of the rod about point O. Okay, torque of the rod about point O. This is how you write it. Torque of rod. Yeah, torque on rod about point O. About point O. Okay. So this is how you calculate torque when rotational values, linear values are given to you. Okay, let's see another example. Okay, very easy. These are very easy. Torque is very easy thing. Okay. Okay, again, this is the situation that the rod is hinged at point O. Okay, it is hinged at point O, and force is applied to it at an angle theta from the rod. Okay, it is at an angle theta from the rod. So let's see. You have to write torque about point O. Again, we have to calculate the torque about point O. So simple. Again, simple. Okay, same thing. Torque. Okay, if you have been given linear forces, okay, linear values. So again, I can write torque as R perpendicular into F. Okay, what is R perpendicular? R perpendicular is the component of R perpendicular to the force. It is perpendicular to the force. So first of all, just draw the direction of force. Okay, force is in this direction. Okay, the L R, you can say the R vector is this. The R vector is this. Now the R vector is not perpendicular in this case. Okay, to make it perpendicular, I will have to draw a perpendicular line like this. Okay, now this R will have a perpendicular component. This R will have a parallel component. It will have a parallel component. I am not interested in the parallel component. I am interested in the perpendicular component. So I need to find this length. I need to find this length. How can I find this length? Let's see. If this angle is theta, you can say that this angle is also theta. Okay, this angle is also theta. Now what you can write simply that this is 90 degrees. So L is your hypotenuse. Okay, L is your hypotenuse and R perpendicular is your opposite side. Okay, R perpendicular is your opposite side. So I can write sine theta as R perpendicular by L. Okay, sine theta as opposite upon hypotenuse. So R perpendicular by L. It is a right angle triangle. Therefore, R perpendicular can be written as L sine theta. It can be written as L sine theta. So I can replace it over here. I can write it as L sine theta into F. L sine theta into F. ठीक है. Now you will be saying कि sir ये तो मतलब you could have written it directly from the formula only. ठीक है ना. हाँ हाँ, that is what I was saying. ठीक है कि why not just write the direct formula RF sin theta. Why I am saying that? Because we were lucky here that theta was given to us in this direction. What would have happened if theta was this theta dash? Okay, what would have happened if your value of theta dash would have been given? Okay, then it would have been RF cos theta. And if you are going with the basic definition, it will become wrong. Okay, basic formula, not the definition, basic formula. Definition is true, definition is still true. Okay, but the basic formula becomes wrong. Okay, so R perpendicular into F is a much, much widely used formula. Okay, much better formula. Okay. Acha, now see here. You calculated it as FL sine theta. No doubt in that it is correct. But if you see, I could have got to the same result in a different manner, in a different method. Just a bit of, just a bit of variation. How? Just see. Write this first. Write this first. Yes, 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 yes. That is what I was going to tell you. Okay. Another way to calculate torque is that you could have taken the components of force. Okay. You could have taken the components of force also. How? Just see. This is your F force. This is your F force. Okay. F force has two components. One is F cos theta. One is F cos theta, and one is F sine theta. Okay. It is becoming a bit congested. So let me draw over here. Okay. One is what? One is F cos theta and the other is F sine theta. This length is L. Okay. Now just imagine that you have hinged your door and you are applying a force in direction of F cos theta. You are applying a force in direction of F cos theta. Will the door move? Will the door show any rotational motion? No, it cannot show any rotational motion if you are applying the force along the center of rotation. This is called as the center of rotation also, you can say, along the point of hinge, you can say. Okay. So if the force is being applied along the hinge, there won't be any rotational motion. So if there is no rotational motion, F cos theta will not show torque because it cannot create rotational motion. F cos theta cannot show rotational motion. So torque cannot be created by F cos theta, but torque can be created by F sine theta. Torque can be created by F sine theta. So I can write the torque again as C. F and L. F and L are perpendicular to each other. Okay, F and L are perpendicular to each other. So again, I can write torque as FL sine theta. F sine theta into L. If you rearrange it, it is FL sine theta. So torque has another way to be seen. Okay, another formula, you can say, another variation. That torque can be written as now R into F perpendicular. R into F perpendicular. Okay. So finally, what is the result which I am having for torque? Okay, you can just note it down. Okay, I have three formulas for torque. One is I alpha, torque is equals to I alpha. Next is R into F, R cross F, in fact, R cross F, torque is equals to R cross F. Okay, four formulas. This becomes four formulas. So this individual formula can be broken down into two ways. Okay, it can be observed in two ways. One is R perpendicular into F, and the other is R into F perpendicular. Okay, so depending on the situation, whichever is easier for you, use that. Use that. Okay, if you can take the components of force easily, then take the components of force. Use this formula. If you are able to take the components of R vector easily, use this formula. If angular values are given to you, use this formula. Okay, so whichever is convenient at that situation, at that instant, you can use that. Okay. Any doubts, anybody? Any doubts? Okay, these are just the basics. Okay, I will show you questions. I will discuss a few questions now on torque. Okay, you will see how the variation is created. Acha. We have not yet discussed the direction also. So just see a direction. It is a very simple way to calculate the direction. Okay, there is a very simple way to calculate the direction. Direction of torque, okay, is represented in anti-clockwise or clockwise direction. Okay, direction of torque is represented in anti-clockwise or clockwise in the same manner as you represent angular velocity. Okay, angular velocity, angular momentum, how you represent. In that same manner, we represent the direction of torque also. Okay, how? Just see here. Just imagine what would have happened just for this first question. Okay, just for the previous example, let's see. If I would have applied a force like this, what is the tendency of the rod? The tendency of the rod is to move in this direction. Tendency of the rod is to move in anti-clockwise direction. Okay, so what we do is, instead of showing it as a vector and anything, we just write in front of the value of the torque, this F into L is the magnitude. Okay, F into L is the magnitude. In front of it, I write it as anti-clockwise. Anti-clockwise. So the direction of the torque is also defined by the direction of the motion of the rod. Okay, by the direction of the motion of the rod. Suppose in this case, in the second question, you can see that F cos theta is not creating any rotational motion. So torque for this force is zero. Torque for this component is zero. But what about F sin theta? F sin theta is creating some torque. It is creating a torque of FL sin theta. It is creating a torque of FL sin theta. So if you see the torque, okay, if you try to push the rod in the direction of F sin theta, okay, the rod will rotate in this direction. It will rotate in this direction. So I can say that FL sin theta is in anti-clockwise direction. Okay, the torque due to F sin theta is in anti-clockwise direction. Okay, so just you have to see how the rod will move if that force is applied on the rod. Okay, so write this. I will show you another example. Okay, in which there will be two different torques. Okay, then you will be able to differentiate correctly. Okay, I guess everybody has written this. Yeah. Acha. Just see another question. Okay, here now you have to find the net torque about point O. Okay, here you have to find out the net torque about point O. Okay, so see here, there are two forces here. There are two forces here, and both the forces are capable of producing torque. Okay, both the forces are capable of producing torque. So just solve them one by one. Just solve them one by one. Okay, let's take the F force first. Let's take the F force first. If we are talking about the force F, okay, torque due to that will be tau 1, you can write it as, okay, torque 1. So torque due to this force will become FL by 2. FL by 2, because you can see that these two are perpendicular. F and L are perpendicular into F. If you write, it will be FL by 2. Okay, no doubt in that. Now forget any other force. Forget that on the rod 10F is acting. Just forget it. If only F force is acting on the rod will move in which direction? The rod will move like this. The rod will move like this. So the direction of torque will be in clockwise direction because of F force. So tau 1, torque 1 will be in clockwise direction. It will be in clockwise direction. Okay. Now let's talk about 10F. Okay, I have not yet talked about 10F. We have not discussed anything about 10F. So now when I am writing torque due to the second force, that is the 10F force. Okay. So again you can see that L and 10F are perpendicular to each other. So R perpendicular into F. So 10F into L will be the magnitude. Okay. What about the direction? What about the direction? When you are writing the direction because of this force, forget that F force is acting on the rod. Okay, just concentrate on 10F force. If 10F force is acting on the rod, it has the tendency to move the rod in anti-clockwise direction. Yes, yes. Okay, it has the tendency to move the rod in the anti-clockwise direction. So therefore, the torque due to the second one will be considered in anti-clockwise direction. It will be considered in anti-clockwise direction. Now, what about the net torque? Okay, you have to write the net torque also, because they are asking the net torque about point O. Na? So if they are asking net torque about point O, just take any one of the direction as positive. Okay, so let's say that anti-clockwise direction is positive. Just you can take clockwise positive also, no problem in that. Okay, if anti-clockwise direction is considered as positive, So I will write this as minus FL by 2. Okay, because T1 is in clockwise direction, it is in the opposite direction. So minus FL by 2. And anti-clockwise, tau 2 is in the positive direction. So plus 10 FL. Plus 10 FL. So this comes out to be 20 minus 1, 19 FL by 2. Okay, so the net torque, you can say the net torque is coming out to be plus. Okay, if net torque is coming out to be in the plus direction, therefore I can say that the net torque is 19 FL by 2 anti-clockwise direction, in anti-clockwise direction. Okay, even if you would have said clockwise direction is positive, na, still the answer would have been this. How? Just see. Suppose clockwise direction I would have considered as positive. Just for example. Okay, I'm solving both over here. Next time I won't do this. Okay, suppose it is positive in this direction. So net torque can be written as clockwise direction as positive. So plus FL by 2. ठीक है, and anti-clockwise direction is negative, so minus 10 FL, minus 10 FL. ठीक है, so if you solve this you will get minus 19 FL by 2, minus 19 FL by 2. Minus sign is representing what? That your net torque is in the opposite direction to clockwise. So therefore here also I will write the net torque as 19 FL by 2 in magnitude, and direction is anti-clockwise, that is opposite to clockwise direction because of the minus sign. Okay, so it doesn't matter whichever you are taking it as positive or negative. Okay, just stick by that method, stick by that sign. Okay, if you are taking anti-clockwise as positive, stick to that sign. Okay, it was coming out to be positive, that's why I said it is anti-clockwise. It is coming out to be negative, so it should be opposite of clockwise. And in the second case, so you can go with that. You can understand the logic over there, that what should be happening. Okay, so this is how you can calculate torque. Okay, the net torque on an object, the net torque on any rotational motion. Okay, hope it is clear. Yes, any doubts, anybody? Okay, so this is the basics. Okay, this is the basics of torque. Acha, now once you have learned about torque, okay, 5 minutes are there. Just we can do the theoretical part. That is equilibrium. Okay, now you can understand what is equilibrium. Okay, now you can understand what is equilibrium. Okay, so just it will not take much time. Equilibrium. Now see, everybody knows, you already know that equilibrium is what? That the net force becomes zero. Okay, that is only a part of the equilibrium. Okay, that is only linear equilibrium. Okay, that is only translatory equilibrium. Okay, so now when we are discussing about equilibrium, there will be three types of equilibrium. There will be three types of equilibrium. Okay, first is translatory equilibrium. Translatory equilibrium. Okay, what do you mean by translatory equilibrium? That only net force is equal to zero. Net force on a body, when it becomes equal to zero, it is translatory equilibrium. Second is your rotational equilibrium. Rotational equilibrium. What do you mean by rotational equilibrium? That only net torque is becoming equal to zero. Okay, net torque is becoming equal to zero. And the third is your equilibrium, only equilibrium, or you can say the net equilibrium. It is also called as net equilibrium. Okay, if somewhere it is written only as equilibrium, you have to understand that it is net equilibrium. What do you mean by net equilibrium? That both torque as well as F net is zero. When both the values are equal to zero, it is called as total or net equilibrium, or simply equilibrium. It is in equilibrium. Okay, so from now on, after this chapter, whenever you see equilibrium, you should get in mind that it means that rotational as well as torque as well as net force is
So what is
zero.
third one?
Equilibrium, just equilibrium, simply equilibrium. Equilibrium. ठीक है, it is called as simply equilibrium. ठीक है, the equilibrium. ठीक है.
Yeah, it's not very clear.
My voice is not audible.
So not very clear.
अच्छा, not very clear. ठीक है, no problem. Just wait. ठीक है. So what I'm saying again, ठीक है, I will say it a bit slowly. That the third one is called as only equilibrium. ठीक है. Whenever we say now that a particle or an object is in equilibrium, that means we are talking about the third case. Third case means net equilibrium is there. Net equilibrium means torque as well as force are equal to zero. Both are equal to zero at the same time. ठीक है. So just write this. ठीक है. You have another class after chemistry class. ठीक है. So we will discuss this in that class. ठीक है. What do you mean by the three different types of equilibrium? ठीक है. We will discuss it in detail because this is very important. ठीक है. And after that we will do a few questions and we will move on to rolling motion. ठीक है. So if you want you can write it. ठीक है. I will zoom out. है ना. So write this and then that's it for now. ठीक है. Today you have another class. ठीक है. At 1 I guess. I don't know the timing. I have to see the timetable. So whatever it is. ठीक है. After
12:15.
12:15. ठीक है. So most probably it is 12:15. So from 12:15 we will have another class. ठीक है then. Thank you. Thank you.
Thank you, sir.
Sir.
Thank you, sir.
Thank you, sir.
Thank you. So I guess everybody has written this. Okay, so I'm ending the meeting.